Hello and welcome to lecture 20. So we're going to continue talking about the mean value theorem. And that is the following statement. So if f is continuous on B and differentiable on the open interval a to b, then some c in the interval a b, we have that f prime of c is equal to f of b minus f of a over b minus a. And as always, it comes with a picture, and this is the picture. So if this is A, let's let this be B. So if we draw the line segment that connects A, f of A, to B, f of B, what do we see? A line segment like this. And the slope of this line segment, this secant line, will be given by how far up we go, divided by how far along. So it's going to be given by this quantity. Okay. So the statement exactly says that we can find point C where f prime of C is equal to this number, right? And if we take the tangent line, then its slope is given by f prime of C at the point CF of C, right? So this means that we can find points on this graph whose tangent line is parallel to this line. Sure enough, that's true. We can just see it. Ready? Cool. So this, as I'll hope to convince you as we go on, is a very natural statement that people who have never heard of the mean value theorem nevertheless know is true. This is simply a common sense fact. If we rephrase it into the language of position and velocity, okay, so we consider f to be the position at a certain time, okay, between A and B, then f prime is the velocity, right? And this quantity right here, f of b minus f of a, is how far we travel in this period of time from A to B, right? Because where we are at B minus where we are at A, so it's how far we travel, huh? Or more accurately, that's how far we travel forward. Yeah? And this thing right here is the time interval. So this divided by this is how far we travel over the time interval, which is the average velocity. Yeah? And the statement of the mean value theorem is that there is some velocity between A and B, at least one, but possibly many more, such that our instantaneous velocity at that time is the same as the average velocity. And of course, we believe that, right? That's obviously true. So I said this is a kind of a joke at the end of the last video, but let's take it a bit more seriously. If from Cincinnati to Dayton was 100 miles, let's assume it is just for simplicity, and if somebody drives that distance in 1 hour, then their average speed will be 100 miles an hour, and for sure they will be traveling at some moment in time at exactly 100 miles an hour, because if they were consistently going faster than that, then they would arrive from Dayton to Cincinnati in less than 1 hour, right? And if they were consistently going slower, then it would take them longer than an hour. So if you start off on your journey from Dayton and you're going less than 100 miles an hour, you're going to have to speed up in order to arrive there in 1 hour, right? So as you speed up, you're going to cross this point where your velocity is 100 miles an hour, because at some point you're going to have to be faster than 100 miles an hour in order to get there, you know, within 1 hour. And conversely, if you're going faster than 100 miles an hour, at some point you have to slow down, otherwise you'll arrive there too soon. So everybody knows this, right? You can convince anybody of this, even if they claim they know nothing about math, because it's just common sense, right? And all this is a description of this principle with the precision of the language of maths. And this precision gives us stuff. Precision has value in itself, as we'll later find out. Okay, so this is the statement. Now, let's do some kind of classical type exercises to test it. So the first exercise is kind of a rather a simple exercise. So suppose f of x equals x to the 3 minus x on 0 to 2. Show that there exists C in 0 to 2 such that f prime of C, let's put this back, equals f of 2 minus f of 0 over 2. Okay, solution. Okay, so this you should recognize as being exactly the statement of the mean value theorem. So let's try and visualize this function a little bit. It's not strictly necessary, but it's just always nice to have some idea what we're doing. So this, for very small x, is going to be smaller than this, so the function is going to start by going down, right? If you take x is a quarter, for example, a quarter to the power 3 is 1 over 64, right? 4 times 4, 16 times 4 again, 64, yeah? And that's a lot smaller than a quarter, so it's going to originally go down, and then it's going to go up. It's going to cross at 1, and it's going to go up like this, right? And at 2, it's going to take the value 6. Now, this is not a very good diagram, okay, whatever. This takes the value 6, yeah? And then what's it asking for? What's this quantity? This quantity is the slope of the secant line connecting where we start to where we end. So it's the slope of this line. And it's saying there must exist some C such that the derivative of the function is equal to this slope. Yeah, for sure it's true. That's just the mean value theorem, and then find it. So the mean value theorem is useful for you in this context in that you know there must be such a solution. There must exist such a C. So a solution, this is what we see. Let's just calculate the derivative. F prime of x equals 3x squared minus 1. What is that slope? F of 2 minus f of 0, f of 0 is 0, f of 2 is 6, so it's just 3. So let's find the x such that x equals 3. That's equivalent to saying that 3x squared minus 1 is equal to 3, which is equivalent to saying that x squared is equal to 4 over 3. And then the solutions are plus or minus 2 over root 3. Minus is not interesting because we're looking for the value between 0 and 2. So C is equal to 2 over root 3. And that's it. Easy. Okay, let's do something that is a bit more relevant. Let's do this. This is a more kind of a typical example of a question testing the mean value theorem. So this is a second example. Suppose f of 0 is minus 3, f prime of x is less than equal to 5. Then what is the maximum that f of 2 can be? Okay. Solution. All right, so we, as always, are going to draw a picture. So say down here is -3, that's where we start, okay? Let's say this here is 1, and say this here is 2. All right, so we're going to use mean value theorem to do this, but it's not strictly necessary to use mean value theorem. I claim that just your visualization of what's going on, of what the meaning of this stuff is, your common sense will already give you the answer. And I'm trying to encourage you to use that as a first tool and then to do the mathematics, the calculation afterwards. I'm unhappy with my 3. Let me do my 3 again. Okay, so let's think about it. All right, so the derivative is always less than or equal to 5, right? And I'm perfectionistic about my letters. Right? And we want to see what's the maximum f of 2 can be, right? And, well, if we want to create a function that grows as fast as possible upwards, right, with this constraint, it's going to be one where the derivative is always equal to 5, right? And that itself is a linear function, you know? So let's draw that. So what happens if we just take a linear function, okay, with slope 5, and we start at -3? Well, if we do that, then when we're at 1, since we're going along by 1, we must go up by 5, right? So we'll be here at, say, 2. So this is 2. So the function will look kind of like this, right? And it keeps going up with that slope. So right here, this is 2. It's going up with that slope. Up here, it's going to go up by another 5, so that'll be 7. I'm not sure how visible this red is. Let me try this one. That's better. Okay, and what we know about our function, we know that the slope is always less than or equal to 5, right? So it cannot be growing as fast as this, yeah? So it has to live underneath this particular red line. So our function, whatever it's doing, it starts at the same place, but it's always underneath. Sometimes it's growing at the same speed, but no matter, it's always underneath in terms of slope, so it cannot be growing as fast. So at 2, it's always going to be less than whatever this thing is. Yeah? So our common sense, our visualization of the situation tells us we expect that f of 2 is less than or equal to 7. Okay? Let's think about this in terms of velocities. Suppose we have a car and its position is given by this function f, okay? And let's call this t instead of x because we're more happy to work t as time rather than x for time. So suppose its position is for f of t, and t is between 0 and 2. And we know the derivative is less than 5, okay? So that's saying that the velocity of the car is less than 5, whatever it is. Let's say it's miles per hour, very slow-moving car, yeah? And then our question is, given that the velocity is less than 5 miles an hour, and we start -3 miles back from whatever particular point, right? How far forward are we from that point if we run the car for 2 hours? Yeah? Well, if we're 3 miles back from it, our maximum speed is 5 miles an hour. Yeah? The car that does go at the speed of 5 miles an hour, which is the maximum it possibly can, will be ahead of our car, right? It will be ahead of our car, and after 2 hours, it will be exactly 7 miles forward, right? Because in the first hour, it'll go from 3 miles behind to 2 miles forward, and the second hour from 2 miles forward to 7 miles forward, right? So f of 2 will therefore have to be less than 7. Yeah? And again, this is common sense principles everyone would agree with, whether or not they know any calculus. Yeah? Cool, so we are really confident that it's less than 2. But this tool of the mean value theorem allows us to express this rather emphatically and rather precisely in the language of math, because what does the mean value theorem say? Well, by the mean value theorem, what do we know? We know that f of 2 minus f of 0 over this thing is equal to f prime of c for some c in this interval 0 to 2. Yeah, but f prime of c is always got to be less than or equal to 5. So from this line here, we are reading off what we can do to explicitly get the upper bound, because all we need to do is multiply both sides by 2 and put this f of 0 on the other side, and we're fine, right? Because f of 0 is just minus 3, so minus minus 3 is just 3. So, i.e., we have that f of 2. Now I'm going to put in what f of 0 is. Again, it's minus 3, so now we have minus minus 3. f of 2 plus 3 is less than or equal to 10, so I've multiplied both sides by 2. Yep, then I put it on the other side. So f of 2 is less than or equal to 7. So the math confirms our pictures, our intuition, we get the same answer, right? And in this case, you might be going, okay, well, I was absolutely sure it was less than 7 anyway. Wasn't this all just a bunch of unnecessary stuff? And that's a good point. Yeah, I was completely sure as well. But as we go forward in maths, there will be times when we think something is true because of our picture, because of our intuition, but we can't see it as clearly. It won't be as simple as that. And there's a real advantage to be able to carefully write down the steps of your thinking using whatever principles you are using. Yeah? So when you are arguing this and trying to explain this to somebody without any calculus, you are implicitly using a principle like the mean value theorem, but you're not actually saying it, you're actually explicitly saying it. Having it explicitly stated and stating it how you're using it is a way to be really sure you've got the thing correct, you haven't misunderstood something. Just in the same way as when you do algorithms, when I'm going over the algorithms that students are doing, plenty of times they're making mistakes and they're not sure how, and I'm saying, okay, let's break down each bit of the calculation into smaller pieces that we're certain of, right? And if we do that, if we write out all the pieces, then we can see where we're making some sort of error, some sort of jump, which isn't correct, right? If you have something you believe is true and you can break down the logical steps of why you think it's true, express them in a concise language where you can look over it and show it to someone and they can follow your logic too, that is a real advantage. And that's the power of this language. So that is the kind of exercise we do with the mean value theorem. That's a kind of classic example. So if you're asked to do this for a free response, you will not, if you did something like this and gave some explanation from this diagram or speaking about velocities, you unfortunately won't get all the points, even though from my perspective that would be totally valid reasoning, because we want you to use the mean value theorem to finally nail that down. There are other mathematical tools you're going to learn later, fundamental theorem of calculus, for example, where you can also argue this. But those are going to come. For the time being, the only thing we know for sure, because we've explained it to you, is the mean value theorem, so you're going to use that in your explanation. You know? Cool. Because, believe it or not, in this explanation with velocities or with growth to do with the slopes, we're implicitly using something called the fundamental theorem of calculus, but you'll learn that later. All right. So that's the kind of example you can expect to see. Let's see if there's some other example. Yeah. It's not really an example, but it's kind of a consequence of the mean value theorem. That's pretty important. So, here's a theorem. Suppose f prime of x equals 0 for all x in this open interval a to b, then I'm going to conclude something about f. Okay? Now, a good thing to do if you're watching at home and weren't in the in-person classes today is to pause the video and try and draw examples of functions on some interval a to b where the derivative is always equal to 0, and then tell me what you conclude about these functions. Okay? Pause the video, draw some pictures, try and tell me what these functions have to be. Okay? Do that now, and once you've drawn these pictures and understood what you think the function should be, press play to hear me talk about it. Okay, so what do these functions have to be? And these functions is constant. Okay, and that should be no major surprise, right? Again, the metaphor of thinking about, well, it's not really a metaphor, the reframing of this as thinking about f as position, and therefore f prime is the velocity. If the velocity is 0 all the time from a to b, then we're not actually moving anywhere, so our position is constant, right? However, this perfectly natural, reasonable thing everybody believes, we can now really make precise with the mean value theorem, because we do this thing which I talked about last time of arguing by contradiction, right? Suppose not. So, for some x1, x2 in AB with, so these labels x1 and x2 are arbitrary, so I can just decide that the x1 is the smaller one. We have f of x1 is not equal to f of x2. Okay. Arguing by contradiction. So we're supposing the thing that we think is true is not true, and we're going to deduce consequences that will ultimately lead to a contradiction. And then from that, we'll say, okay, we actually have to have that it's constant. Okay. This is a very efficient way to argue things. So let's draw a picture. So it could be, and what hopefully you drew is just a function that is flat, right? But maybe there's some weirdness that it can, you know, it can be a tiny, tiny little thing somewhere where there's a little tiny kind of like up or down or something, or maybe it does something like this where it just, you know, does something like this, just goes up and then goes back to being flat, right? And maybe it happens on a really, really tiny scale, yeah? But let's check. Well, if that's true, then let's call that point here x1, and let's call this point here x2. Yeah? And then what? Well then, because f of x1 is not equal to f of x2, this is not equal to 0, this number here, the difference between the two. And also, x2 is bigger than x1, so this number on the bottom is well defined, it's non-zero, so this entire expression is a non-zero, well-defined number. Yep. But this is also the slope of this little tiny secant line connecting these points. Yep. So this is also equal to f prime of c for some in this interval x1 to x2. Yeah? But that's a problem. But f prime of c has to equal 0, because that's the assumption. Every point inside that interval has derivative 0. So we know that this is not equal to 0, and it's equal to the derivative, but f of c equals 0, contradiction. Okay. So the initial assumption that we have 2 points for which f of x1 is not equal to f of x2 cannot be true. Just cannot be true. Okay. Now another thought question. We have that the statement that the derivative of f is equal to 0 for every point in a b implies that f is constant. Okay, that is this statement. Yeah, we have this statement implies this statement. I'm going to underline in green. Okay, so if we call that statement A, we've shown that A implies B. Here's my question for you. Is it true that B implies A? Okay. Again, if you have to pause it, think for a second, ask yourself if that's true. And then unpause and watch my explanation. Okay, so what is the reverse statement? The reverse statement is that a constant function has 0 derivative. Is that true? Yes, it's true. Right? If we have a constant function and we differentiate it, for sure the derivative is 0, right? So if f of x equals c, then f of x plus h minus f of x over h is always equal to 0, so the limit as h goes to 0 is only 0, so f prime of x equals 0. Yeah? So plenty of times we have some statement A that implies B, and I'm asking you if B implies A, and I'm showing you it's actually not true because I'm trying to get you out of this habit of, in case you have it, of assuming that if A implies B, then B implies A, right? Which certainly isn't logically the case all the time, but in this case it's true, right? So don't automatically assume that whenever A implies B, B does not imply A. Sometimes it does, in this case it does, okay? Cool, all right, so we have this cool statement, and again you might think, well, that's pretty obvious. All right, well, let's do another statement, which is very similar but a bit more general, and this is one which we'll use later when we talk about integration, and that's the following result. So suppose f prime of x equals g prime of x for all x in the interval AB. Then there's a relationship between f and g, and I want you to tell me what it is. Okay, so then whatever. So again, I want you to tell me what it is, and this is how you're going to figure it out. You're going to take a piece of paper and you're going to draw functions f and g over some interval a to b with this property that the derivative at every point is the same. Yeah? Draw examples of pairs of functions f and g with this property. Look at what you see, and then figure out that relationship, and then try and express that relationship in the language of math. Okay? Pause the video, do that, and then watch me do it to see what we come up with. Okay. Well, then, well, let's see. Let's draw some pictures. Where do I have space? Let me erase a little bit and give myself a bit of space. Let's use this space right here. All right, so we have some interval a to b. And suppose we have this as function f, right? That's something like this. This is f. And suppose we have function g. It's doing something. So the slope's always the same. So trying to copy the slope. So obviously a relationship between f and g, right? We can just see it, right? And you might be saying, okay, well, f is just g shifted downwards, right? Or g is just f shifted upwards, right? But how do we express that? How are we going to shift it upwards? Well, shifting f upwards is like adding some constant value to f, right? And if we look at this more closely, sure enough, it looks like whatever value we have here, the gap between g and f is going to be the same, right? So the statement is that f of x equals g of x plus c all x in AB. Okay, and this is a theorem, so I should say theorem. And then why? Well, we believe it from the pictures. Yeah? We can, again, use the reframing or reformulation of this stuff in terms of velocities. If we do that, then suppose we have car A, whose position is given by F, and car B, whose position is given by G. I'll write that down. Looks like I've written a name there. Car A, and this would be car B. Then what is the statement that f prime equals g prime? That's exactly the statement that the velocity is the same over every time in interval a to b, right? So you have two cars whose velocity is exactly the same over some time period a to b. Then at the start time, whatever distance they are apart, because f again represents the position, right? F is the position of A and G is the position of B. So whatever distance they are apart from the start time, at the end time B, they have to be the same distance apart, which again makes sense to us, right? If you are looking at a Formula One race and you have car A is in pole position and car B is 50 positions back, whatever, I don't know, like 500 meters behind, right? But they run the race and they are always, at every moment in time, going exactly the same speed over exactly the same course, right? Then when they cross the line, or when they stop, let's put it that way, when they stop, then they'll still be at exactly the same distance apart. Yeah, they'll be the same distance apart throughout their entire race, and when they stop, or better to say, when we look at time B, they will still be exactly the same distance apart. So this is another common sense thing that everybody will believe and know, but again, we're expressing this in the language of math, and we are confirming why it's true with our language, and in this case rather easily, because what do? We just look at this function f minus g. So if we take the derivative, and it's just equal to f prime minus g prime, which is equal to 0. So this new function f minus g satisfies this hypothesis of the previous theorem. So f minus g is equal to c on AB. So it follows in basically one line from the previous result. And later, I mean, some of you already seen antiderivatives, right? And this is why antiderivatives are different by a constant, and can be different and are different by a constant, because when we differentiate them, we don't see that constant, and if we have two antiderivatives of the same function, then that means both those antiderivatives have the same velocity, so they must differ by a constant. So this later on is a rather important fact for us, but that's to come later in this course. Okay, so these are all consequences of the mean value theorem. So the mean value theorem is principally a conceptual thing to test, and it is testing a rather common sense thing that that whether or not people are aware of it, they actually do have in their heads. And it has some nice consequences. It tells us some important facts rather easily. So you should be expected to be tested on your understanding with questions like this, with questions about finding the points explicitly where the mean value theorem holds true, where f prime of c is equal to f of b minus f of a over b minus a, and other kind of formulations of that statement. But the main thing is it's a conceptual statement. So yeah, make sure you understand why it's true, why you see it's true. And that's the main thing you need to take away from this. Okay, so I'm going to erase the board and then leave this topic and move on to the next topic, which is going to be the differentiation, or what the derivative of functions tells us about the graph of a particular function. And it's, in many ways, a very related thing to what we've just done. So that's coming up after I clean this board. Okay, so how f prime affects and I suspect that's not how you spell fx. Apologies for the misspelling. All right, so let's start with the simpler stuff. So suppose f prime is positive on some interval a, b, okay? At this point, the meaning of derivative should be burned in your brain in a completely indelible way. You should know that the derivative is expressed like this because of this picture. So this side is h, and this other side is f of x plus h minus f of x. Okay, now time to put it in. The slope of this hypotenuse here for some small h is given by this. We take the limit as h goes down to 0. That is the infinitesimal slope of the graph at that particular point. That should be absolutely in your bones at this point. Okay. So what do you notice about this? Well, if the function, or if the derivative is increasing, therefore the slope is positive, and if that's true for every single point, then you see a graph that is increasing over that interval. Yeah? Going back to the metaphor of velocity, not the metaphor, the reformulation in terms of velocity. If you have over some time period A to B, the velocity of the car is always positive, then the car is always moving forward. Yeah? Its position away from its start point is always increasing. Yeah? So we know this is a fact. Yeah? That if the derivative is always positive, then the function is always increasing on that interval. And conversely, if this thing was negative, then the thing would be sloping down. So if we did this kind of picture, we had a graph like this, did this picture, so here is x, this is x plus h, this is the point x f of x, this is the point x plus h, f of x plus h, okay. then what is this? This thing here is h, and then what is this? This thing is okay. But in this case, if this thing is negative, because obviously h is positive, then that comes with the graph sloping down, right? And therefore the graph is decreasing, right? So we see that if the derivative is always less than or equal to 0 over some interval, then it's actually decreasing over that interval from this picture. Yeah? Again, reformulating as velocities, if your velocity is negative for over some time interval, then you're going backwards. Yeah? Cool, so that is our first principle from the pictures, straightforwardly, and let's write it down. So, increasing, decreasing test. So, if f prime of x is bigger than 0 for x in interval a, b, then f is increasing. On a, b, in fact, it's reversible. Conversely, if f is increasing, then f prime is going to be bigger than 0. Okay? And if f prime of x is less than 0 for x in b, oops, that's not how you spell thin. F is decreasing. On a comma b. So that's our first basic thing that we're learning about how the graph, how the derivative affects the graph of the function. Let's do an example to solidify this. Okay. Example. F of x is equal to 12 x to the 3 minus 12 x squared minus 24 x on the entire real line. Find the intervals of increasing, decreasing. So from now on, increasing, decreasing will be written like this to save writing. Okay, solution. All right, we've just learned that we can do this by looking at the derivative. So obviously we're going to calculate the derivative. So differentiate this thing. We have 3 times 12. Let me check I got the numbers right, because that looks like a rough thing to calculate. I didn't get the numbers right, because this isn't the function, it is a derivative. So, example. Let's write that again. Suppose the derivative is given by this. find the intervals of increasing and decreasing of f. All right, so we don't have to calculate the derivative because it's given to us. But we need to know when it is increasing or decreasing, which right now is kind of a pain to try and understand. So what we're going to do is we're going to try and factor out this expression. So what do we see? We can factor out 12x straight away, right? So then we're going to have x squared minus x minus 2. Okay, and that's way easier because now it's going to be x minus 2, x plus 1, right? That's not 12, this is 12x. Okay, cool. All right, and now that's very helpful because it tells us where f prime is equal to 0. It's 0 at 0, it's 0 when x equals 2 and when x equals minus 1. So let's draw a picture. Let's do it over here. So we know that it's going to be 0 at minus 1, at 0, and at 2. Okay? Yeah, so this is meant to be a picture of the entire real line. And why is this useful? Well, it's only 0 when that's the case. So from minus infinity to minus 1, the derivative is not 0, and it's a continuous function. The derivative is just a polynomial. So if it's not 0 from minus infinity to minus 1, it's either going to be positive or negative. It can't go from positive to negative from minus infinity to minus 1 without crossing somewhere, and it doesn't, right? So it's either going to be positive or negative from minus infinity to minus 1. And for the same reason, it's either going to be positive or negative from minus 1 to 0. It can't cross between minus 1 and 0 because that's the structure of it. It's only going to cross here, here, and here, right? So it's either positive or negative all the way from minus infinity to minus 1, positive or negative from minus 1 to 0, positive or negative from 0 to 2, and then positive or negative from 2 to infinity. So we can break down the behavior of this thing into these sub-intervals. How many do we have? 1, 2, 3, 4, right? And each one of those will be positive or negative, and we just have to figure out what they are. Yeah? So you could just take some particular number in each interval and plug it in and hope you get it right. But that's actually not the best way to do it. That's most likely to get it wrong. So this is how you should do this, and I really recommend you do it this way because this is the kind of exercise that's really easy to get wrong. So create a table like this. So create table. Again, that's not how you spell this word. Okay, so here's a table. And what we're going to do is we're going to put the factors of this derivative in this table. So let's put this 12x part here. And let's put this x minus 2 part here. And then let's put this x plus 1 part here. And then finally, let's put this f prime here. Okay? And on this side over here, let's put the various intervals we're interested in. So our first interval is from minus infinity to minus 1. The next part is from minus 1 to 0. The next part is from 0 to 2. And the final part is from 2 to infinity. Okay. And then we're going to fill out this box with the sign of each factor. So here, we're going to put a plus or minus depending if this factor is positive or negative in this region. And it's easy to see that from minus 1 to minus infinity, it's negative, right? Here, from minus 1 to 0, again, negative. Here, positive. Here, positive, okay? And let's fill out the rest of this. So here, from minus infinity to minus 1, and we subtract 2 for definitely negative, right? Here to here, again, definitely negative. Here to here, now again, negative. We have to be a bit more careful But if we have a number which is strictly less than 2 and we subtract 2, it's definitely negative, so we've got a minus. And then here, a number which is strictly bigger than 2 and subtract 2 is positive. Yeah? Cool. All right, here. We have a number which is strictly less than 1, and then we add 1, it's still going to be negative. Now we have something which is actually bigger than minus 1, and we add 1, so now it's positive. Here's positive, positive. Easy. Now, the sign of the actual derivative of f prime is the sign of each of these factors, right? Because these are just, for each x, these are just numbers with either positive or negative sign. So the sign of the ultimate thing in the end is just the product of all these numbers, right? So we have a negative number minus a negative number times a negative number times a negative number. It's got to be negative. Negative times positive, got to be positive. Positive, negative, positive, got to be negative. Positive, 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 got to be positive. Cool. So we now know that from minus infinity to minus 1, this thing has got a negative slope. Yeah? Start again. Yeah, it's got to be sloping down because the derivative is negative. Then it's got to be sloping up. Then it's got to be sloping down. Then it's going to be sloping up. Yeah? So, we don't know much else about it, but we definitely know it is. So I'm just going to put in some rough information here. It is definitely sloping down like this, and then it's going to be sloping up, and then it's going to be sloping down, and it's going to be sloping up, right? And later on we'll be able to figure out how to do a much better, more convincing graph, right? But that is basic information that we can read off with this table here. Cool. All right, so we can find out, given the derivative, the intervals where it's increasing or decreasing with the increasing, decreasing test. Now, we're going to talk about using the derivative to identify whether we have a local max, a local min, or nothing above a critical number. Okay? So, suppose C is a critical number. Of f. Now, we have various cases to consider, right? So, let's first try and get some kind of a picture what we think is going to happen if we have a local max. This would be our graph. Again, I don't like this line. This better. So this is our critical number, right? If we have a local max, then what happens? Then we have something like this, or perhaps it comes up peak and it's not smooth, but this is what we see happening, right? This is what we see happening. So what about the derivative? So take your hand, and with your holding your hand flat, show the slope of the local max. So the slope is like this, so it's a positive slope, positive, positive, and then it's flattening out at the top, and as we cross C, it's no longer positive, it's going down like this, right? Because this particular critical number I've drawn is where the derivative is 0, right? So slope positive, less and less positive, is slope 0 at C, and then down like this. But we don't have to just have that, right? We could also have a critical, this is another one, let's call this one C1, this is C2. We could have something like this. That would be another local max, right? But we still have this phenomenon, right? We have positive, 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 then we hit the local, then we hit the critical, and then when we reach the critical number, suddenly we're now negative, 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 right? Take your hand and do this. What you see when you do this, the flat of your hand is indicating the slope of the tangent line is that it's positive, and then as we cross the critical number, it's negative. Positive, negative, positive, negative. Yeah? So, suppose C is a critical number. If near C we have that f prime goes positive, negative, as we cross C, then local max at C. Yeah? Okay, so we underline that all this stuff is about identifying what's happening above a critical number. Now, on the other hand, if near C we have that f prime goes, let's figure out what happens if we have local negative. So this is local max. Let's figure out what we have when we have a local minimum. I should have said. So here, local min. What does that look like? Well, it's either something like this, or perhaps there's a sharp peak like this. Yeah? That's a local min. Let's take our hand again and do this thing. So the flat of your hand indicates the slope. So the slope is going to be negative, 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 negative. And then it's going to hit 0 on this guy here, where the critical number is such that f prime of C1 is 0. So negative, negative, negative goes to 0, then positive, 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 right? Negative to positive. And if we have a critical number where the derivative doesn't exist, negative, positive, negative, positive, negative, positive. Yeah? In both cases, negative, positive. Okay? So f prime goes negative to positive. Then what? Then f has local min. Let's see. Okay. So this is, let me call this principal. This is like 1. This is 2. Now, if we have nothing happening, so it's not going from, it's not a local min or local max, because as you guys know, critical numbers don't necessarily live underneath always a local max or a local min. It can be just underneath something where neither of those things are happening. But then what happens? Then it kind of looks like this, right? Yeah. So example. F of x equals x to the 3. Cool. So what happens when we have something like this? Well, it's going positive, 0, and then positive again. Yeah? So this is not local min or max. Could be something like this, or it could be something that goes down, flattens out, and goes down again, right? Which would be something like this. Yeah? So, this is our third principle. 3. if near C f prime goes negative negative or positive positive, then not local max or local min. Okay, so this gives us a tool, and this is called the first derivative test, because we're just using the first derivative to identify at any critical number whether or not we have a local max, a local min, or nothing. And all we have to do is just look at the behavior of the derivative as we go across this critical number, right? And it's just pitches, right? If, as we go across this number, we go positive then negative, we can see that that has to be a local max. If we go negative to positive, then for sure it's going to be a local min. Or if we go positive to positive, or negative to negative, then nothing. Yeah? And that is the main thing people get wrong, believe it or not. So people try and apply this without understanding which of these things means what, because I tried to memorize it because they have no picture at all, right? And they get it wrong. But if you have a picture, then this is completely impossible to get wrong. You can just see it, right? So when we have in-person exams, there'll be a room with 200 students, and so like walking around, standing from the front, see some people like this, and they would be my students because they are checking for themselves, once again, that they've got it right. You're going positive to negative local max, negative to positive local min, like this. Yeah, so get in the habit of verifying for this for yourself, get it right. I sometimes have to do this with my hand myself, so that you apply this test correctly and identify the local maxes and local mins. All right, let's use this on the example we've calculated, right? Because we have critical numbers at -1, at 0, and at 1. We've drawn a picture already, but let's try and ignore that. Forget this picture. Let's just use this principle. Yeah? So let's look right here. So as -1 is a critical number, and as we go from -1, we are going from negative to positive, negative to positive. So we expect a local min. And now let's look. Yep, sure enough, local min. So this is negative to positive. Put it local min. Look over here. So next one is at 0, and we're going from positive to negative, positive to negative, positive to negative, local max. Let's look, sure enough, local max. So this here is positive to negative, and this is a local max. Finally, at 2, we have negative to positive, negative to positive, negative to positive. Yeah? Local min. Let's look. Yes, sure enough. Negative, positive, and this is a local min. So we can identify all these things rather easily. This is a natural, straightforward test, right? Cool. All right. So in the next lectures, we'll be using more properties of the derivative and the second derivative to understand features of the graph that follow from these information about the derivatives in a manner rather similar to this. It's going to follow very naturally from our pictures. So if you've been doing everything I've asked of you, if you've been visualizing this thing, training yourself to turn this language, which is a language that describes pictures, into pictures, if you're used to doing this, you will find this next section very natural and very straightforward. And if you haven't been doing this, you will find it less so, but here's your opportunity to catch up, because this is where the payoff increasingly comes. Okay, so that's it for today. Have a great weekend. I'll see you all next week.